So now we move to spatial autocorrelation per se. And I call this global spatial autocorrelation because it's one coefficient for the whole map. And what this coefficient basically will tell you is this map spatially random or is there some kind of structure to it? And then I introduce a particular device called the Moran Scatter Plot, which will allow us to make some sense out of this in terms of interpreting the association and classifying into different types, some of which are clustering, that's like surrounded by like, and some of which are outliers, which is value surrounded by dissimilar values. So we could have high incomes surrounded by other high incomes, like we just saw with the near north, or we could have low incomes surrounded by other low incomes. Those are clusters. And then we can have the opposite, where high income is kind of an island surrounded by low incomes, or low income surrounded by high incomes. And that I call a spatial outlier. This is not necessarily an outlier in the sense that we saw before, which is in value space, attribute space in the box plot. But this is relative to the neighbors. So that's the concept of a spatial outlier. So what I'm first going to do is create what is called a spatially lagged variable. And the spatially lagged variable is nothing but the average of the neighbors. So for each observation, we're going to compute the average of the neighbors, and we're going to store that as a new variable in our table. Okay. So we go back to the calculator. I'm going to add a variable, and I'm going to call it W underline inc per cap, and we're putting it next to the other two for income per capita. No, here it is. I'm going to put it here between random income and the original income per capita. So we'll have our table as another blank column. Okay. Now we're going to construct that, and as it happens, we have this in the calculator under this tab here called spatial lag. If you click on the spatial lag tab, you see the weights. If you go through this list, it gives you all the weights you currently have active, or I should say available. The one that with the check mark is the active one. So this is queen contiguity. It's going to look at the immediate neighbors and compute the average. The new variable is this W inc per cap that we had. Here it is. And the variable that we're computing the spatial lag for is income per capita. You leave this alone. We use row standardized weights. That assures that it's an actual average of the neighbors. So we're averaging the neighbors. If you apply, then of course our blank column gets filled. And now we have the average of the neighbors. And what I want to do is I want to look at our original map here, and I'm going to map, just like I did with the random ones, quantile map 6, and I'm going to pick the average of the neighbors. W income per capita. If you do OK, this is a map. And in some places, it looks very much like the original map, and in other places, it does not. Okay. What does that mean? If we go here, for example, all these locations are in the top category. The average of the neighbors is also in the top category. Is that likely to happen by chance? Probably not. Right? But here, we have a different situation. Say, for example, this one the original is high, the average of the neighbors is not that high. There's another one here, which is in the higher category. The average of the neighbors is not that high. Right? We have low-income community areas, average of the neighbors, low-income community areas. So this is what we're trying to quantify. You know, we can eyeball it, and maybe with 77 community areas, you can more or less tell what's going on. If you do 800 census tracts, eyeballing is going to become difficult, right? So what we're going to do is compute Moran's I, which is a spatial autocorrelation coefficient, and we use a particular device to both compute it and visualize it. And that device is called the Moran Scatter Plot. So this is something I came up with. It's this icon here. See Moran Scatter Plot. You can also get it from space. If you go to space, univariate Moran's I, that's what you want. Or here, univariate Moran's I. We won't talk about multivariate anything today. Okay. So not W income, but income per capita. That's the variable. We make sure that we have the weights. So what's going to happen now? As it turns out, this is an algebraic result. The Moran's I spatial autocorrelation coefficient is the slope of a regression line in a scatter plot of the spatially lagged variable on the original variable. So X on the horizontal axis, WX on the vertical axis. It just turns out to be that if you standardize the variables. So that's what the Moran scatter plot does. It standardizes the variables. So these are standard deviational units. It draws the line and it gives you the coefficient of the slope. This is Moran's I. Okay. Is this meaningful? And there's a big difference between a spatial autocorrelation coefficient and a regular correlation coefficient. Regular correlations, you know, or if you don't, you'll find out soon, are between 1 and -1. Right? Spatial autocorrelation coefficients depend on the weights that you use, because that's how we compute them. You can see it right here. We have the spatially lagged variable. With different weights, you will have a different spatially lagged variable, and you will have a different slope. So the slope itself, not that interesting except for the sign. What is interesting is to what extent is this a slope that we could have had randomly or not? And to that, we use randomization. So randomization is shuffle, but shuffle many, many times. So if you click on here and you see randomization, you see the number of permutations. And what I'm going to do, I'm going to go down to 999 permutations. What does this do? Under the hood, shuffle 999 times. Then for each of these shuffled maps, you can think of them as maps, it computes the spatially lagged variable, the average of the neighbors on the map, and computes Moran's I. Does this 999 times and compares it to the one that we just computed. That makes it a nice round number of 1,000. Of these 1,000 cases, how many are more extreme than the Moran's I that we observe? Right? So you click on this. This is a histogram of the 999 shuffled Moran's I's. And what we see is that our green bar, that's the one that we just computed, is nowhere near this distribution. So if you ask any reasonable person, is this a Moran xi that could come out of a spatially random distribution? You would say no. What you can do here is actually quantify that by saying the chance that it comes out of a spatially random distribution is 1,000 or less, 1/1,000 or less. Now be careful, this is called a pseudo p-value. If you've taken stats before, you know about p-values. Those p-values come from analytics. A pseudo p-value comes from computation. So the pseudo p-value depends on how many of these permutations you do. If you only do 99, the smallest pseudo p you can get is 0.01, not 0.001. If you do 99,999, which is the maximum in GeoDa, you will get a very small number. That doesn't mean that one is more significant than the other, okay? So you have to be very aware that a pseudo p-value is not really a p-value. It's kind of a shortcut to summarize this distribution, to summarize the fact how many from this distribution are more extreme than the green that we get. So of course, what we're going to do is do this again. Here we go, Moran xi, univariate Moran xi, and I want to do this for my random income, okay? So we pick the random one, same weights, do okay, and we get this little flattish line. We go randomization 999, and we get a totally different distribution. Now we get a distribution where 16, almost 17% of the shuffled maps have a Moran xi that's actually larger than the one that we got here, right? Most reasonable people would say that is not extreme enough for me to reject what is called the null hypothesis of spatial randomness. So this is really not that different from spatial randomness. It better not be, because we created it as spatially random. Right? So that is the logic behind this pseudo p-value. It's a shortcut to say, well, how much, here's our green bar, how much is larger, equal to or larger than our green bar in a spatially shuffled world. If this green bar is in the middle of the browns, you have no or very little evidence of systematic patterning. If, on the other hand, like we had here, the green bar is way outside, we do have evidence of systematic patterning. That is the rationale. So what we do, we have a variable, we select the spatial weights matrix, we pick univariate Moran xi, we get this graph, and then we do randomization to make sure that the slope that we get is a meaningful slope. In this case, because there's not very many observations, a slope like this will not be very meaningful, but in very much larger data sets, it might be. So you always have to do the randomization. Okay. Let's go back to our original income per capita and income per capita map. Now let's select a variable. And let's select this one. This is a brown one surrounded by all brown. We have very high income, that's on the horizontal axis, and the average of the neighbors is also very high. This is an example of clustering, grouping together of similar values. The clusters are on the main diagonal. The ones in here, and look carefully what I do, are dark values that tend to be surrounded by dark values. The other way you can see it is if you go to the spatially lagged map, these will tend to have the same colors. Okay, so the map, this map is for the spatial lag. That's the average of the neighbors. This map is for the original value. The graph shows us the observations in the upper right, whatever it is, segment. This is what I call high clusters. Okay. Here we have the yellows, and for the neighbor, we also tend to have yellows. Again, this is the average of the neighbors. The average of the neighbors is very similar to the original value. Those are clusters of low values. I call them low. You have to keep in mind that this is all relative to the mean, the center. So if you're looking at, say, income per capita, you want to know what this mean is, because below the mean may not be that low. It depends where you are. And if you're in Beverly Hills, below the mean is not low, right? If you're in Alabama, below the mean is low, but above the mean is not high either, right? So always put it into perspective relative to what that mean is. It's really, rather than high and low, I should say above the mean, below the mean, but it's a little awkward, right? So those are the clusters, high, low. Then the off diagonals are high values surrounded by average of the neighbors that are below the mean. I call this high, low. And if we look at the maps, this one is the best one. Dark, not so dark. So this is the top category out of 6, and this is the 4th category out of 6. So this is a high-low spatial outlier. Relatively high income per capita, surrounded by neighbors. So this is an interesting case because the neighbors to the south and the west are higher, but the neighbors up here are much lower, right? And if you know Chicago, this is Beverly. And it's a bit of an outlier out there. And then the final group is this one. Again, we go to the maps. And this is low, high. This one is the best one. Second category, surrounded by 5th category, average of the neighbors. So those we call spatial outliers. And then, of course, what you want to do, so backtracking, we have the Moran Scatter Plot. This is nicely divided into 4 categories. Upper right, high, lower left, low, lower right, high, low, upper left, low, high. Spatial outliers, spatial clusters. So you can separate them out. Next week, remember, I don't say anything about significant. Next week, we will move from this to actual significant clusters and significant spatial outliers. And to close, one thing I want to show is sensitivity analysis. So we just very quickly do this again. Univariate Moran Xi, the income per capita, but we're going to take the 6 nearest neighbors instead of the queen contiguity. And okay. You have with the queen, we had 0.601. Now we have 0.499. Oh, you might say, this is much less correlated. Be careful. I said the correlation can only be interpreted by knowing the weights. We have two different weights. These numbers are not comparable. If you remember anything from this class, they are not comparable, okay? So what you need to do instead is go back to this randomization, and what the randomization gives you is not only this graph, which is basically the same as before, but it gives you this z value. And what the z value is it takes the distribution, it computes the mean and the standard deviation and standardizes the Moran xi. And the standardized values are comparable because you've taken out the influence of the weights. So if we go back to our other, which one? This one here. So here we have a z value of 8.58, and here we have a z value of 8.82. Much closer, almost identical, than the original Moran xi were, which was 0.601, 0.499. You would say, well, one is more correlated than the other, which is your natural instinct, but it's not. Because you have to bring in the weights. The weights, by computing the standardized z value, you correct for the weights. The z values are comparable. So if you do this for your project and you use different weights, always go back to the z values before you say that one is more correlated than the others. Where is our random one? Here we have a z value of 0.985. So way lower.